Welcome to this video on thermodynamics, where we calculate the amount of energy needed to melt a 1 kilogram block of ice at negative 19 degrees Celsius and then heat up the water to 100 degrees Celsius. What is the heat energy required to heat and melt a 1 kilogram block of ice initially at negative 19 degrees Celsius into 1 kilogram of water at a final temperature of 100 degrees Celsius? And we're going to assume there's no vaporization in this problem. The specific heat capacity of ice is 2,108 joules per kilogram Kelvin. The specific heat capacity of water is 4,182 joules per kilogram Kelvin. And the heat of fusion of ice is 3.34 times 10 to the 5 joules per kilogram. For this question, we're going to assume the melting point of ice is exactly 0 degrees Celsius. To stay organized in these type of questions, I like to break things up into their different components dependent on whether we're within a phase or we're undergoing a phase change. In this question, we have three components. We have the heating of the ice, which goes from negative 19 degrees Celsius to the melting point of ice, 0 degrees Celsius. We have the transition in phase from ice to water, so we'll call this ice water. And during this transition, the temperature remains at 0 degrees Celsius. And finally, we have the heating of the water. And this goes from a temperature of 0 degrees Celsius to 100 degrees Celsius. So a key distinction when we're doing questions like this is what's happening in each segment, because this helps us choose our equation. In the first segment here, we're heating. All the heat energy added goes towards increasing the temperature of the ice from negative 19 degrees Celsius to 0 degrees Celsius. This is similar to our last segment where we're again heating. All the heat energy added to the water is used to raise the temperature from 0 degrees Celsius to 100 degrees Celsius. In the middle segment here, we undergo a phase change. So in this segment, all the energy added is used to convert ice to water. None of the energy is used to increase the temperature of the water. So in a phase change, all the energy is used for changing the phase, melting the ice, turning it into water, and the temperature remains the same. We're now ready to pick our equations for our respective segments. In the segments where we're heating and undergoing a temperature change, we use the equation Q is equal to mc delta T. So here, Q equals mc delta T. Similarly, when we're heating the water, Q equals mc delta T. When we undergo a phase change, we use the equation Q is equal to mass multiplied by heat of fusion, because the phase change we're undergoing is solid to liquid. So Q is equal to mHF. If we were vaporizing water, we'd be using the equation Q is equal to mass multiplied by the heat of vaporization. Another benefit to breaking these questions up into segments is that we don't have to add a bunch of small subscripts to stay organized. We realize that we're working with ice here, so this is the mass of the ice, the specific heat capacity of the ice, and the change in temperature of the ice. So it just saves us some time and keeps us more organized. So we start by solving for the heat energy required to bring the ice from a temperature of negative 19 degrees Celsius to 0 degrees Celsius. And Q is equal to mc, and the changes in temperature is equal to temperature final minus temperature initial. Substituting our values into this equation, we have Q is equal to the mass of the ice, which is 1.00 kilograms, multiplied by the specific heat capacity of ice, which is 2,108 joules per kilogram degree Kelvin, multiplied by the temperature final, which in this case is equal to 0.00 degrees Celsius, subtract the temperature initial, which is equal to negative 19.0 degrees Celsius. The two negatives here make a positive, so if we rewrite this, we end up with Q is equal to 1.00 kilograms multiplied by 2,108 joules per kilogram Kelvin multiplied by 19.0 degrees Celsius. Multiplying 1 by 2108 and by 19 gives us a final Q equal to 4.0052 times 10 to the 4 joules. And we'll keep all the decimal places for now to avoid rounding errors. You may be wondering what's going on with the units here. Well, our kilograms on top cancel with our kilograms on the bottom. And here you'll notice we have Kelvin on the bottom and Celsius on top. This will often happen if we're working with quantities like water, where we give the melting points and the boiling points in degrees Celsius and the initial temperatures in Celsius. But remember, this quantity here is the change in temperature. Now, although degrees Kelvin and degrees Celsius have different reference points for 0, the change is still the same, because to convert degrees Celsius to degrees Kelvin, we're just adding 273. And if we were to add 273 to both of these values and then subtract them, we'd still get the same number here. So in these cases, we can cancel Kelvin and Celsius, leaving us with our heat energy in joules required to heat ice from negative 19 degrees Celsius to 0 degrees Celsius. We're now ready to calculate the amount of heat energy that's required to convert 1 kilogram of ice into 1 kilogram of water. And we already have our equation. Q is equal to the mass of the ice multiplied by the heat of fusion of ice. So we can immediately substitute our values. Q equals mass of ice, 1.00 kilograms, multiplied by the heat of fusion of ice, which we see above is 3.34 times 10 to the 5 joules per kilogram. Since we're just multiplying the heat of fusion of ice by 1, our final Q is just equal to the heat of fusion of ice, which is 3.34 times 10 to the 5, and our kilograms on top cancel with our kilograms on the bottom, joules. So how much heat energy is required to change 1 kilogram of ice into 1 kilogram of water at 0 degrees Celsius? 3.34 times 10 to the 5 joules. And finally, we're ready to calculate how much heat energy is required to heat 1 kilogram of water from 0 degrees Celsius to 100 degrees Celsius. As before, this equation is equal to Q equals mc. Change in temperature is temperature final minus temperature initial. Substituting our values, we get Q is equal to the mass of the water, 1.00 kilograms, multiplied by the specific heat capacity of water, which is 4,182 joules per kilogram Kelvin, multiplied by our temperature final, which is equal to 100 degrees Celsius, subtract our temperature initial, which is 0 degrees Celsius. And this gives us Q is equal to 1.00 kilograms multiplied by 4,182 joules per kilogram Kelvin multiplied by 100 degrees Celsius. Multiplying 1 by 4,182 multiplied by 100 gives us a final Q equal to 4.182 times 10 to the 5 joules. So our kilograms cancels with our kilograms, and again we can cancel our Celsius with our Kelvin, because this is a difference in temperature, and if we converted these to Kelvin, add 273 to both temperatures, we'd still end up with the same difference. So how much energy does it take to heat 1 kilogram of water from 0 degrees Celsius to 100 degrees Celsius? It takes 4.182 times 10 to the 5 joules. And finally, to get the total amount of energy required to heat 1 kilogram of ice from negative 19 Celsius to 0 degrees Celsius, then to change the ice into water, and then to heat the water from 0 degrees Celsius to 100 degrees Celsius, we just have to sum our 3 energies. So the Q total, so the heat energy total that is required to undergo this process is 4.0052 times 10 to the 4 joules plus 3.34 times 10 to the 5 joules plus 4.182 times 10 to the 5 joules, giving us a Q total, if we add all these numbers together, of 7.92 times 10 to the 5 joules. So in summary, how much heat energy is required to melt 1 kilogram of ice at negative 19 degrees Celsius and heat it to 1 kilogram of water at 100 degrees Celsius? It takes 7.92 times 10 to the 5 joules. Thank you for watching this video on thermodynamics, where we calculated the amount of heat energy required to melt 1 kilogram of ice at negative 19 degrees Celsius and turn it into 1 kilogram of water at 100 degrees Celsius.